The Large Hadron Collider is one of the wonders of the modern world. It's believed to be the largest and most complex machine mankind has ever created.
We learned from the Large Hadron Collider the smallest amount it was possible for us to learn.
Scientists have only begun to explore the vast mysteries that exist in the universe, and a group of physicists discovered something that could turn everything we know upside down. They have discovered many new things that require new theories of physics to explain them, with the advent of advanced technology. Leading the charge has been CERN in particular. Scientists at CERN have made a revolutionary discovery that has the potential to alter history and fundamentally redefine our understanding of the universe. What did they find? How will it affect mankind? Join us as we delve into how physicists at CERN just made a terrifying discovery that changes everything. The exciting discovery of Higgs boson. The centerpiece of the European Organization for Nuclear Research, CERN's scientific research, a significant post-World War II European establishment, is the Large Hadron Collider, or LHC. It is a center that attracts scientists from all over the world. Its main job is to accelerate protons to extremely high speeds and smash them together. These collisions take place inside enormous detectors that are positioned in underground caverns, and scientists can examine the results to learn more about a variety of phenomena. The discovery of the Higgs boson excited scientists for a very long time. British physicist Peter Higgs believed that there was a field that made particles heavy in the 1960s. According to him, there ought to be a particle associated with it, and that particle would provide mass to every other particle. The Higgs boson has been sought after, and in 2012, a significant discovery was made at the LHC after years of searching. They discovered a tiny particle in the center of an atom that weighed roughly 126 times more than a proton. Less than a year later, researchers discovered that the new particle they had been searching for was the Higgs boson. They achieved this by methodically collecting a great deal of data, roughly 2.5 times as much as they would have otherwise, owing to the potent Large Hadron Collider. This finding was comparable to locating the final piece of the large jigsaw puzzle known as the Standard Model in the field of particle physics. This model only describes the interactions between tiny objects, such as forces. Gravity is left out. In 2013, Peter Higgs and François Englert were awarded the Nobel Prize for their discovery of the Higgs boson and their subsequent declaration of its existence. Professor Victoria Martin of the University of Edinburgh claims that this discovery solved the puzzle of the Standard Model. It was like the last piece of the puzzle, and it rocked particle physics by letting in previously closed doors. On June 30th, CERN's head of theoretical physics, Jean Giudice, made a daring announcement. According to him, the field of particle physics has evolved more in the past 10 years than it has in the 30 years prior. The Higgs boson's role as a carrier of the Higgs field, much like photons carry the electromagnetic force, is one of the main reasons for the excitement surrounding it. Martin says that this field is fundamental, even more fundamental than the particles themselves. It's like an unseen force that permeates everything in space and time. Thus, certain particles receive their mass from interactions with this Higgs boson, which functions as a kind of symbol for this field. Consider the minuscule mass of electrons or the zero mass of photons. They can travel at the speed of light and essentially ignore the Higgs field. That's not the case for the heavier particles, though. They must struggle through this Higgs field, which causes them to slow down and gain mass. Thus, the Higgs field, this cosmic muck, is what gives those heavyweights in the particle world their mass. Although not much has been observed thus far, scientists are fairly certain that this is the normal course of events in the particle universe. Like those other particles, the Higgs boson is said to obtain its weight through self-absorption. With a mass of approximately 125 billion electron volts, it is 125 times heavier than one of those positively charged protons that are at the center of an atom. This measurement was carried out by the Large Hadron Collider, LHC. Aside from this significant finding, there are still many unanswered questions regarding the Higgs boson. It appears as though the experts have only touched the tip of its potential. What is this instrument that produces the above-mentioned discovery in the field of physics? What's the main gap behind this instrument? The legendary LHC. The incredible Large Hadron Collider, also referred to as the Atom Smasher, has left people in awe of its astounding discoveries and sheer magnificence. The field of knowledge was cloaked in mystery in a time before its founding, with theories that remained unproven and questions going unanswered. A paradigm shift happened with the advent of the LHC. The haze of doubt cleared, bringing with it a new era of discovery and enlightenment that would fundamentally change the trajectory of human history. The famous Large Hadron Collider, housed at the European Council for Nuclear Research (CERN), close to Geneva, Switzerland, resumed operations in April 2022, following a 3-year break devoted to extensive maintenance and upgrades. This momentous occasion marked the start of an extraordinary scientific project known as Run 3. This project has the potential to produce a series of astounding experiments that will pique people's interest throughout the world until 2024. However, CERN has released a troubling statement about turning on the famous Large Hadron Collider. Constructed in collaboration with more than 10,000 scientists and numerous universities and laboratories worldwide, CERN built the largest and highest energy particle collider in the years 1998 to 2008. Located in a 27-kilometer-long circumference tunnel, the LHC is roughly 175 meters below the French-Swiss border near Geneva. The circular tunnel that houses the collider is underground, but it is at different depths ranging from 50 to 175 meters. This intentional depth variation reduces the amount of tunneling beneath the Jura Mountains, preventing the need to build a vertical shaft. This particular tunnel choice lowers expenses and lessens the need for landscape adjustments. Furthermore, the Earth's crust acts as an intrinsic shield against background radiation. The 3 8-meter-wide tunnel was built between 1983 and 1988 and has a concrete lining. The tunnel passes through 4 different locations along the border between France and Switzerland. Despite being mostly located in France, the surface-level facility houses auxiliary equipment such as refrigeration units, control electronics, ventilation systems, and compressors. An estimated 15 petabytes of data were produced annually by the LHC and related simulations. To manage the significant amount of data generated by collisions, the LHC included a computing grid as a fundamental element in its architecture. This made the Large Hadron Collider one of the most expensive scientific instruments ever created during the construction phase, which cost about 7.5 billion euros. Its birth was approved in 1995 with a budget of 2.6 billion euros, of which 210 million euros was set aside for experiments. After being put into operational status on September 10, 2008, the LHC experienced a setback during its first testing phase. A significant amount of damage was caused by a quench incident involving over 50 superconducting magnets, their mountings, and the vacuum pipe. This event resulted in a 14-month postponement, prolonging the already protracted wait. With an energy level of 3.5 tera-electron volts per beam, the LHC achieved its first collision in 2010, almost quadrupling the previous world record. Its energy capacity skyrocketed to 6.5 tera-electron volts per beam after later upgrades. 4 crossing points, where accelerated particles collide, make up the collider. Also, 7 detectors are strategically placed near these crossing points and are expertly designed to pick up on unique phenomena. Even though proton-proton collisions are the main focus of the Large Hadron Collider, it can also accelerate heavy ion beams. Every year, Roughly 1 month is devoted to proton-led and experiment-led collisions. The collider's primary goal is to allow physicists to verify particle physics theories' predictions through experimentation. The collider took an extended sabbatical for upgrades in 2015, following its initial 3-year operation. Following its restart, the operational Phase 2 lasted an additional 3 years, from 2015 to 2018, before another protracted shutdown that lasted until 2022. The LHC was once more reactivated in April 2022, with an upgraded maximum beam energy of 6.5 TeV. It was anticipated that this operational phase would last until 2026. This amazing instrument LHC is an answered prayer for the scientists. But this instrument has made other discoveries too. What are they? Other shocking discoveries of LHC. The LHC finds quarks. Nathan Isger, the late theoretical physicist, shows off a model of a portion of a device that tracks quark behavior. In 1981, the cost amounted to $83 million. The theory that hadrons are composed of 3 different types of constituent particles was independently proposed in 1964 by 2 researchers who were having difficulty understanding hadrons, which are subatomic particles impacted by a strong force. Murray Gell-Mann dubbed them quarks and distinguished between 3 types, or flavors: up, down, and strange. George Zweig referred to them as aces. Later, 3 additional quark flavors, charm, top, and the bottom, was discovered by physicists. For a long time, hadrons were classified by quarks into 2 groups. Mesons, like pions and kaons, were formed by quark-antiquark pairs, while baryons, which include protons and neutrons, were made up of 3 quarks. A peculiar particle known as X, 3872, was also discovered in 2003 by researchers in Japan. It seemed to consist of a charm quark, an anti-charm, and at least 2 other quarks. Z, 4430, an apparent 4-quark particle, was discovered by researchers investigating the particle's potential existence. Since then, evidence for several of these particles has been found at the LHC, breaking, or at least significantly bending, the accepted model for quark arrangements. These Z particles are ephemeral, but they might have flourished for a nanosecond or 2 after the Big Bang. At the LHC, a worker is situated beneath the compact muon solenoid CMS, a general-purpose detector. Some optimistic physicists believed the detector would find evidence in favor of SUSY. Supersymmetry, also known as SUSY, was developed by theorists to address several unresolved questions left by the Standard Model, including the mass of some elemental particles, the possible historical connection between electromagnetism and the strong and weak nuclear forces, and the composition of dark matter. It also revealed an intriguing connection between the bosons that mediate interactions between the quarks and electrons that comprise matter. However, SUSY states that each particle can change into its corresponding boson, and that every fermion has a corresponding boson. Additionally, by allowing corresponding particles to cancel out, it would eliminate certain runaway infinite quantities that arise in mathematics and allow for the possibility of gravitons, a long-theorized gravity force carrier, which is glaringly absent from the Standard Model. Scientists had high hopes for the LHC. Either it would uncover deeper issues that would lead to new experimental and theoretical directions, or it would find evidence in favor of SUSY. Though neither seems to have occurred as of yet, supersymmetry is not completely ruled out. There are numerous variations of SUSY, each associated with specific hypotheses. The LHC has only separated a few of the most sophisticated and plausible versions. At CERN, a hearty quark-gluon plasma is the soup of the day. Scientists operating LHC instruments observed an unexpected phenomenon when they chose to force neutrons into lead nuclei rather than the typical proton-proton collisions. Instead of the atomic shrapnel taking random paths as before, there appeared to be coordination. The impact produced an exotic state of matter known as quark-gluon plasma QGP, which flowed like liquid and produced coordinated particles as it cooled, according to one theory put forth to explain the phenomenon. By colliding heavy ions like lead and gold, Brookhaven National Laboratories and the LHC have previously produced QGP, the densest form of matter outside of a black hole. If QGP from a proton-led collision turns out to be feasible, it may have a profound impact on scientific understanding of the circumstances just after the Big Bang, during which QGP experienced a brief heyday. The single issue is that there shouldn't have been enough energy in the collision to produce the predicted quark soup. Some have argued for a second explanation involving a theoretical field created by gluons, the particles that mediate strong force, and paste quarks and antiquarks into protons and neutrons. Despite the difficulties with this explanation, the majority of physicists still support it. According to the theory, gluons traveling close to the speed of light interact with one another through fields. If this model is accurate, it may offer insightful information about the interaction and structure of protons. An analysis of 600 million particle collisions per second can produce a large amount of data. It's probably safe to predict that many more surprises will be revealed by LHC data. As absurd as it may sound, a lot of physicists were hoping that the standard model would have some flaws that the LHC would reveal. After all, the framework is flawed, and perhaps a game-changing finding would establish supersymmetry, or at the very least lead to new lines of inquiry. But as we've already indicated, the LHC has consistently undermined exotic physics while reaffirming the standard model. Granted, the LHC has not yet reached its maximum energy of 14 tera-electron volts, and the results are not all in, but there is a ton of data to examine. Still, the odds are not in favor of making the conventional model appear unflattering. Or perhaps they do, judging from a B-meson decay report from 2013. It depicts a B-meson decaying into two electron-like particles and a K-meson, also known as a kaon. The Large Hadron Collider has continually revealed or made space for discoveries. Here is another one, a crack that remains open for 14 hours, which causes storms. The unexplained crack. On July 7th, during the third run of the Large Hadron Collider, an odd crack in the Earth's magnetic field was observed. This mysterious crack did not go away like a fleeting flash of lightning. It remained open for 14 hours. This extended opening allowed strong solar winds to pass through, causing significant geomagnetic storms that produced breathtaking auroras. Scientists struggled to look away from the breathtakingly beautiful aurora created by the geomagnetic storm caused by the crack. Interestingly, a rare phenomenon known as a rotating interaction region from the Sun or CAR is responsible for the emergence of this crack. These vehicles are vast plasma structures created in the low and middle latitude regions of the heliosphere, where the solar wind streams mix with fast and slow motion. The solar wind and the Sun's magnetic field are included in the heliosphere. The rotating interaction regions are propelled from the Sun toward Earth in a manner akin to coronal mass ejection. Shock waves and compressed magnetic fields within them can result in turbulent space weather, which frequently takes the form of mesmerizing auroras. This particular circular affected Earth's magnetic field early on July 7th, resulting in a sustained class geomagnetic storm, according to National Oceanic and Atmospheric Administration assessments. Analysts noted that the coronal mass ejection was associated with a nascent wind that precedes a co-rotating interaction region. An important question arises: should the public be concerned about this magnetic field splitting? Experts say there is no need to raise the alarm because cracks in the Earth's magnetic field are relatively common. This magnetic shield protects us from solar storms. Although many cracks in the field open and close quickly, recent events show that these cracks can remain visible for long periods, many hours. In 2003, Harold Freya, the lead author of a study on this phenomenon, compared the Earth's magnetic shield to a house with a window open during a brutal storm. It is mainly the effect of a storm. Part of the energy slips through its cracks, similar to a storm damaging a sofa indoors. Similarly, the magnetic shield normally protects against space storms, but some energy leaks through its cracks, sometimes causing interference with satellite radio, communications, and electrical systems. Fortunately, the fissure did not cause a radio or power outage. Instead, residents of Canada and the United States were treated to eerie lights that underscored its stunning effect. In addition, scientists revealed that the sun is entering the most active phase of the solar cycle, which occurred earlier than expected. This increased activity predicts the likelihood of an aurora sighting within the next 3 years, especially at the Large Hadron Collider. These achievements go beyond magnetic field detection. With the advanced achievement of LHC, there are different opinions and ideas on what this instrument is meant for, and the true intention behind the invention. Due to the effectiveness and achievement of LHC, it has raised different theories and opinions. What are they about? Are they valid? Conspiracy theories about LHC. As the search for answers intensified, so did the concerns of those who questioned the possible results of this divine manipulation. The Large Hadron Collider, an instrument that helps us understand the universe, is stuck in our reality in the face of esteemed fears and nightmarish creatures. Others claim that the LHC has a huge weapon, ready to destroy the entire planet at the flick of a switch. Let us not forget those who see the LHC as an advanced government scheme to manipulate the mind and turn us into mindless automatons. Others argue that the LHC is a deep dive into evil purposes amid such theories. They suggest that the particle collisions inside the LHC are part of a secret government experiment to create a new world order where survival is limited to the elite. At the core of this apocalyptic hypothesis is the concept of a false vacuum, a theoretical space in which energy does not rest. At its lowest level, the potential of a false vacuum is that of the LHC, which destroys everything we value. Although this ultimate scenario may seem far-fetched, it is not quite likely. LHC experiments can create conditions that facilitate the creation of a false vacuum, resulting in the formation of black holes capable of absorbing all the gravity of galaxies, is profound and has the potential to change our understanding of the universe. This scenario imagines the universe collapsing into nothingness, as seen by Thanos in the medieval universe, where half the universe disappears. Although the formation of black holes inside the LHC is unlikely, the consequences of a false vacuum are too threatening to ignore. The Higgs field has to overcome a huge energy barrier by quantum tunneling into an energetic state. The sheer scale of this barrier is so great that the transition would probably require a time much longer than the age of the universe. While the theoretical collapse of the universe is alarming, its practical consequences are not immediate. The Higgs field is flexible and temporarily confined to a false vacuum state. This means that although the threat of a doomsday scenario is real, it is not an immediate threat. The instrument held lots of mysteries in its working as much as its discoveries. What are these findings? And how will they affect our world? Exceptional discoveries of LHC. In July 2017, many analyses based on Episode 6 Collection 2 were presented to the public as an actor who thoroughly studies the properties of the Higgs boson and increases the accuracy of various results. In March 2021, LHC experiments revealed 59 new hadron discoveries in data collected during the 2 initial operational phases of the collider. A remarkable red rock, 2 runs 2 miles, shows your observation of a new type of pentaquark, including the charm quark, charm antiquark, up quark, down quark, and strange quark. This revelation came from observing charged B mesons that decay with time. The results of each experiment in particle physics gradually decrease, while the first best results are gradually achieved. As the years pass, the yield of discoveries decreases proportionally. An obvious strategy to correct this phenomenon involves upgrading the instrument, especially in terms of collision energy, luminosity, and detector improvements. a possible collision energy increase of 14 tera-electron volts is even being considered. This upgrade, known as the Large Luminosity Hadron Collider, was initiated as a priority goal in June 2018. Its brightness improves the prospects for rare process detection and statistical refinement of fringe measurements. The third run of the LHC is set to be an intermediate step in this comprehensive program. One highlights the long-awaited major discovery of the Higgs boson. Later, 2 Higgs bosons showed significant decay, confirming its role as a source of mass. CERN's ambitious plans for a third run of the Large Hadron Collider demonstrate the commitment of the scientific community to push the boundaries of our understanding. Doubling the current dataset and increasing the collision frequency tenfold are significant advances in experimental particle physics. These efforts provide scientists with more opportunities to study rare phenomena, strengthen existing theories, and search for new physics that is out of the ordinary. The extended downtime planned for 2029 demonstrates the commitment to careful planning, maintenance, and upgrades to ensure the reliability and safety of the LHC, the world's most powerful scientific tool for this type of instrument. A full LHC with an increased collision frequency promises to reveal new particles, forces, or phenomena that may have gone unnoticed in earlier times. Thanks to these ongoing efforts and technological advances, we are getting closer to answering some of the universe's most profound questions. This marks the beginning of the 12th cycle, leading to the expected 4th, the 04 data set nearly 10 times larger than expected, at the peak of the 3rd cycle. Looking ahead, the upcoming 4th round of the LHC promises to strengthen and expand the theories and assumptions that can emerge from the experiments and analyses of the research. This sequence of drives represents the gradual progression of the LHC program, where each stage develops independently to make uninterrupted scientific discoveries. Looking to the horizon, the culmination of the Large Hadron Collider effort shows that the mysteries of the universe have been explored more deeply. The development part of the LHC summarizes gradual progress and tantalizing revelations as it moves into the 3rd round and beyond. Each run contributes little by little to the body of knowledge, systematically expanding the horizons of our understanding and providing unprecedented access to the hidden complexity of the universe. Although the journey is one step at a time, it has the potential to change our understanding of the inner workings of the universe. The initial chronicle of the LHC program brings to life the spirit of scientific research, which methodically unravels the deep secrets of the universe. Driven by the dedication of brilliant minds and the remarkable capabilities of the LHC, Round 3 is central to this story, laying the groundwork for future publications and insights, enhancing our scientific journey. As the expedition continued, the world watched with anticipation and eagerness to see the next chapter in the story of the Large Hadron Collider and the discoveries of real physics. The cosmos yet holds another shocking secret, which is a field that interacts with particles. Let's delve into the tale. The advent of the Higgs field. After the Big Bang, the cosmos was a turbulent mixture of particles, energy, and radiation. However, as the universe cooled and expanded, an extraordinary change took place. At that moment, the mysterious Higgs field, an energy field that permeates space, was activated. This field interacts with particles as they pass through it, giving them mass. The use of a penetrating Higgs field is necessary for particles to have mass. Without this interaction, the particles would lack mass, resulting in a universe vastly different from the known reality. The structures we observe would not be realized. Here comes the Higgs boson, a particle intrinsically bound to the Higgs field. Imagine the Higgs boson as the universe's solution to the weight problem, providing the necessary mass for all other particles. However, the importance of the Higgs boson goes beyond its role. Without the Higgs field, particles would travel at the speed of light, preventing the existence of atoms, molecules, chemistry, and biology. Without the Higgs field, Elementary particles would remain exposed to eternal light, unable to slow down or rest. The discovery of the Higgs boson marked a significant advance in particle physics, culminating in the awarding of the Nobel Prize in Physics to Peter Higgs and Francois Englert in 2013. Indeed, the quest to unravel the mysteries of the universe continues, and the possible existence of a fifth fundamental force adds another layer to the chat portal investigation and ongoing physical research. The universe remains one of the most enigmatic entities known to science. Understanding its nature and properties is a physicist's priority, and the search for this knowledge can lead to the discovery of new forces or interactions that could help explain mysteries. The Higgs boson, often called the God particle, plays a central role in understanding particle physics and the fundamental forces of nature. The existence of the Higgs field sheds light on the mechanism by which particles acquire mass. Our knowledge of the Higgs boson is deepening and may hold the key to unlocking further mysteries of the universe, including the nature of dark matter and the possible existence of extras. What do you think about these discoveries? What are your thoughts about this amazing instrument? Let us know in the comment section. While at it, share and subscribe to the channel for more related content.